Is post-exercise stored lipid oxidation, healthy fat burn, actually a physiological protector of muscle glycogen? In sports domains, the phenomenon of excess post-exercise oxygen consumption, or EPOC, occurs because we intentionally utilize carbohydrates during anaerobic tension. EPOC metabolism is an oxygen-intensive recovery phase following acute anaerobic exertion, wherein the body shifts to systemic lipid oxidation to restore cellular balance and resynthesize depleted muscle glycogen, typically lasting between 12 and 48 hours, during which the body maintains an elevated state of oxygen consumption to restore cellular balance. In the recovery phase, it is suggested that the body performs a metabolic prioritisation to manage carbohydrate fuel source. According to Farinati, 2016, carbohydrates are actively diverted toward glycogen resynthesis following exercise, which forces a systemic shift toward lipid oxidation during EPOC. Based on this, we explore the cellular recovery mechanism known as EPOC and the metabolic shift it may initiate. With intense mechanical tension, the working tissue requires energy faster than oxygen can be supplied, thereby creating a metabolic deficit. High-intensity anaerobic work generates a significantly larger cellular disruption than steady-state endurance activities. Once the mechanical tension ceases, the body's immediate biological priority is not energy expenditure, but cellular restoration. It is suggested that this requires an elevated rate of oxygen intake, referred to as excess post-exercise oxygen consumption, or EPOC. During this EPOC window, an intricate metabolic prioritization occurs. Under healthy conditions, to preserve what remains of the localized carbohydrate store, the body actively halts the burning of muscle glycogen. It engages the Cori cycle. The lactate generated as a byproduct of anaerobic glycolysis is shuttled to the liver, where it is metabolically recycled back into usable glucose. This means the byproduct of mechanical tension is actively repurposed to begin restocking the stores. However, observations suggest that driving this highly energy-intensive recycling process requires a completely different fuel source. Instead, every available carbohydrate molecule, including the glucose actively recycled via the Cori cycle, is prioritized for repletion. The localized muscle store must be restocked. However, this mechanism is highly energy-intensive. To meet the high ATP demands of this systemic recovery, while simultaneously securing carbohydrates for the muscle, the body optimizes its fat stores, utilizing lipid oxidation to fund the rebuilding of carbohydrate reserves. On the other hand, steady-state cardio burns fat in real time to meet aerobic energy demands. However, anaerobic tension burns carbohydrates intra-workout, shifting fat oxidation to the recovery window. If the defining characteristic of this recovery phase is an intense systemic oxygen demand, it follows that nutritional intake might be optimized to support oxygen transport networks. So, hemoglobin and myoglobin rely heavily on iron to function. Incorporating iron-dense, complex carbohydrates, such as red lentils, may offer a highly efficient physiological alignment to gradually restock the muscle stores, trace iron to support long-term oxygen transport as part of a combination, and a dense matrix of antioxidant and anti-inflammatory nutrients to manage the acute oxidative stress generated by mechanical tension. Holistically, understanding this metabolic shift demonstrates that our nutritional choices do not just replace burned calories, they provide the structural architecture required to sustain the oxygen demand of true physiological recovery and growth, and real nutrient-dense foods interjected within these mechanisms may elevate their efficiency. Based on individual suitability and health status,